Rose theorem now right here, and we can switch the order of these, right? So what I'm going to do here is I'm going to leave this guy the same, this dot, and then I'm going to pull that over here. Okay, now you'll notice we have something that kind of looks like a derivative of something, right? To make it more explicit, I'm actually going to write it out. So we're going to add 0 in the middle here, right? And we're going to add a special 0. So s squared s dot. And I think, let me make sure I add the correct one. We're going to want, the partial of q with respect to s, and then the partial of s dot with respect to s. Plus this guy. And I'm going to convince you this is 0. Okay, so we're good with the fact we're assuming s dot and s are independent, right? So this guy is technically 0. So all I've done is I've added 0. I haven't changed anything, right? But now watch this. So I'm going to claim that this is the derivative of this. S dot plus dq dt. Let's check me on that, right? So derivative of the first thing with respect to this gives you this times the second. And then this thing times the derivative of the second thing, well, that's going to be that times the derivative of this with respect to this, which we noticed is 0, right? And then the derivative of this with respect to this gives you that, right? So we know we've created this this derivative here, and we've been able to kind of undo that step there. So, okay, now we're going to recognize what this is. In fact, if we look over here, I should sort of suggestively use the color green. But this guy right here, this is in fact this guy, right? It's exactly the same. So we know this is actually q dot, right? So in other words, this whole thing right here is actually q dot. Q dot with respect to s. Okay. So
what we've done is shown that the partial with respect to s commutes with the total time derivative.
Yep, exactly. So now that we have that, though, we can go back and we can substitute. We were looking at this part of our equation right here, right? And now we got it in terms of this. So now, as a final step, we're going to come, well, almost final step, we're going to come right over here. So we have partial L, partial Q, partial S, plus partial L, partial Q dot, partial Q dot. And this is the result we just got, partial S. All right, nice. Okay, so we're going to pay attention to this. This is our first result. Now remember, this was specifically the left-hand side of, where was it? Over here. This is this guy right here. So we just figured out the value of this. So now we're going to figure out the value of this. So I'm going to come over here. Let's see if we can do green again, I guess. So we're going to take a look at this guy over here. So we have partial L, partial S. Now remember, L is in terms of Q, which is in terms of S and T, and then Q dot, which is in terms of S, S dot, and time, and all in terms of time. Because if we wanted that, we have that option. Okay, now the partial derivative is going to be, we can just use, again, the chain rule. So we notice L depends upon Q, and Q depends upon S. We notice L depends upon Q dot, and Q dot also depends on S. And I think that's it, right? That's what we wanted. Okay, now if you notice, if you compare this and this, they're the same. What that means is that this statement right here is in fact true. So we have shown that we did a variable change, and we ended up getting the Euler-Lagrange equation for that new coordinate system, so QED, right? So this is a more complicated way of doing this. If you notice, we had to use several assumptions. We had some continuity assumptions and some other things, right? Those are kind of the motivating factors here. Now, we're going to simplify this argument a little bit, because we're going to talk about, instead of these differential manipulations, we're going to talk about action, because you can also make an argument in terms of action that's a little bit simpler than this. So I'm going to erase this stuff. Okay, so let's remind ourselves what action was defined to be. So we said that if we have some Lagrangian, we can define action from a first time to a second time as the integral from the first time to the second time of the Lagrangian over time, right? Something like this. So it takes some q and it gives us some value for it, right? And if you remember, we, I think the last time I presented, we talked about how if you make this assumption that the variation in this action is 0, then that implies the Euler-Lagrange equations, right? So we're gonna,
Together with some boundary conditions, right?
well, yeah, with some other details, right?
Yeah.
Plus stuff, right? We're being formal. So this is where we got this from. So now what we're going to do is we're going to think about, well, so all we've done here with our coordinate transformation is we have these new explicit dependencies in here, right? And what I mean by that is basically L of Q, Q dot, and T is now going to be L of Q, which is in terms of S, and T, Q dot, which is in terms of S, and S dot and T, and then T, right? And so, in fact, what if I just call this, L with a different version of L, basically, that's equal to this version, but it's in terms of just S, S dot, and T, right? I'm allowed to do that as well, right? So, we notice that this is actually equal to the original for some time, right? Because since these are in terms of time, basically, if I was to draw little dependency trees, right? So L, we know, depends upon Q and Q dot, and Q and Q dot in turn depend upon T, so something like this. And then L itself can also depend on T. So ultimately, I have some time, this will be a certain value, right? Now, if you'll notice, L hat, since L depends upon T, at the same time, these will actually be, not L hat, but I don't know what we want to call it. Tilde. Yeah. L squiggle, I like that. So at the same time, so if I chose like T1 for this one, these will actually have the exact same value, right? And that's just because of the way this time dependence works, because I haven't changed my time coordinate. So this allows us to go up here and make a simplifying assumption. Well, so these are equal for all values of T, right? So in fact, what I could do is swap this guy out for the same action, but maybe we'll call it S squiggle, right, suggestively, because it's in terms of the other guy, T1 to T2 of L squiggle, which is now in terms of S, S dot, and T.
Did you want the argument to be S?
S squiggle S.
Did you want that? Or?
Yes,
Okay.
I did want that.
Okay.
Okay, so, and all I've done here, so technically, this is actually equivalent to this, right? In fact, I could just drop this right here, and this is still a true statement, right? Because basically, this guy is equal to this guy because of this point by point thing that we just discussed. And so this is really cool because this implies this, but this doesn't care about, this argument we made last time about how this implies this doesn't care about the coordinates we used, if we remember right. We just had some arbitrary variation in the function and we ended up getting the Euler-Lagrange equations. So, and in that case, in terms of these, thus, the argument is, and I'm not going to go into the details because we already did this last time, but basically if you do that same variational calculus on this version of things, well, you get the exact same answer, but you would get it in terms of this. And so notice, again, we get ddt of this partial, L hat. And I guess this is the same as the original L, so we could actually write it either way. S dot, that is going to be that. Okay, and so in other words, we get the same thing right here. Now, this argument's maybe a little bit more hand-wavy because we didn't go into the details of this, because we did that previously, but hopefully this is an easier way of understanding why it should still be true if we go to new coordinates, right? The idea is because ultimately changes of coordinates don't change the time coordinate, then we end up getting kind of the same action, and so this implies that the Euler-Lagrange equations, which were a result of a little bit of variational calculus, will still hold over here, if that makes sense. And this is the more explicit version of that, right? We went through and we actually showed that that was the case. So there we go. So that is why, in our case, we can do changes of coordinates that are really useful. In fact, you can choose any kind of reasonable, is what we talked about, changes of coordinates that have a certain sense of like continuity and being, I think they need to be invertible too, we talked about that. Yeah. But they allow us to do really useful things like this. And so, anyway, yeah, I guess that's
cool.
That's what I had to present on. So
thank you
guys.
It's great.
So is the Euler, thinking about it from this perspective, are the Euler-Lagrange equations a special kind of differential equation?
Yeah, I mean, because like that's a miracle that you get the same form. That is there's something very, very special about the Euler-Lagrange equation.
Yeah.
Well, what is it?
It's whatever you just saw there. But yeah, so what's the really deep reason why that is? I don't know. I mean, my question would be, it would be something vague at first, but it would, I would try to make it,
I think it has to do with the part that is a little bit more complicated, which is actually the variational calculus. And I don't pretend to have taken even a variational calculus course, but I think digging into this part of things would help you understand better, because this is a lot of tricks, right? This is a very tricky proof, I'm gonna flip things around and pull stuff out. So, but this one is kind of it has to do with the fact that you have this space you're embedded in, where at certain times t you have different values and you kind of integrate between them. And so somehow that's always the same kind of idea, no matter what coordinates you're choosing for that system. I think it has more to do with that, if that makes sense. I don't know if that answers your question, although maybe.
Yeah, I guess maybe
think about it.
Yeah, I wonder if it has something to do with the fact that because it ultimately sort of comes from
a variational principle.
a variational principle where
Yeah.
well, in particular, I wonder if it's in some way related to the fact that your action is an integral of something, and so on a certain fundamental level, I guess that's with t and not with your coordinates, but because it doesn't care what t is, it's kind of t is just the dummy variable. I wonder if in some way that ends up playing a role where if you derive, but obviously t is not the coordinate. Kind of the whole point of this is you weren't changing t. So
and I think that's a good point. My guess is that if I was to mess with t, it might not work, and that's specifically because now I actually am changing how my action is defined, right? Because I somehow wasn't changing the integration parameter between these two definitions. I was just changing the other ones, which we talked about this ultimately still depend on t, right? So that's the thing. I think changing t might actually change your action. You might get something weird, but I haven't tried it, so that'd be something interesting.
Yeah, well, what's interesting about that, I guess, along those lines, it's almost like with the assumptions we made, it's sort of as you pointed out, it's L is what it is at a given point in time, regardless of how you decide to express it, And so when you look at it from that perspective, well, it's sort of well, of course, not of course exactly, but it's maybe not surprising that the Euler-Lagrange equations doesn't change, because there's a clear sense in which L fundamentally isn't changing despite your change of coordinates.
Exactly. It's L is kind of this function that exists, and you can express that function in terms of different things, but it doesn't change the function, and so we should expect that some property about, I don't know, we describe these paths along that function kind of somehow doesn't change when we change coordinates. Kind of weird though, but yeah.
I'm also wondering, if you try to, if you do a change of coordinates, with Newtonian, in the Newtonian formalism, I'm wondering if there's a regular, if there's a clear part of it that stays the same, but then you get this part that gets added onto it or something like that. And then, I'm wondering, I wonder if it would be instructive to try to change coordinates in a very generic sort of Newtonian
kind of framework.
Framework and see what happens, and that might help you see that's why it doesn't change with the Lagrangian formula. I don't know.
And I guess going back to this example right here, part of the reason we do like these change of coordinates is, for example, we were talking about this before today, but there are things called Lagrange points, if you've ever heard of those, in orbits. And so I'm not going to place them where they're supposed to be, but they're kind of, I think these are them, right? So there are these points in orbits which are stable, and this is with respect to a fixed reference frame of the orbiting body, right? So if the Earth-Sun system was stationary, and instead you had some sort of fictitious centripetal force going on, you could put a potential energy field here, do the Lagrangian mechanics, and you'd find these are saddles or basically stable locations, right, in your space. And so what's interesting is, for example, this one